The aim of a supply chain is to deliver materials at the right time to the point they are needed. The importance of short-term schedules is that they give the timetables for making these deliveries. However, the schedules do not just show the times of deliveries, but organize all the other resources, including equipment, people, materials, facilities, and everything else. These schedules say exactly when materials are needed, so managers can use them to make sure that they are ordered, purchased, and delivered at the right time. Then the schedules give a means of controlling the flow of materials through supply chains. Managers know when tasks have to be done, so they do everything needed to make sure that things actually occur at the specified times, effectively controlling the associated flows through their supply chains. Designing short-term schedules. The aim of these short-term schedules is to organize the resources needed for the master schedule, giving low costs, high utilizations, and other measures of performance. Managers do this by adding details to the master schedule. This is one of the most common jobs in every organization. Whenever you go to work, fit an appointment into your diary, travel somewhere, go shopping, cook a meal, or almost any other job, you have designed a short-term schedule. When you get up in the morning and go to bed at night, and virtually every job in between, you are working to a schedule. In practice, people often use scheduling rules, which are simple rules that experience suggests give reasonable results. You see examples of scheduling rules in banks, which schedule customer service in the order first come first served, or hospitals, which schedule emergency care in the order most urgent first. Schedulers use many such rules for their specific needs. We can illustrate this with 4 common ones. For this, imagine that you have a number of jobs waiting to use a piece of equipment. Reasonable suggestions would take jobs in the order first come, first serve. This is the most obvious rule and simply takes jobs in the order they arrive. It assumes no priority, urgency, or any other measure of relative importance. It is perceived as fair, but has the drawback that urgent jobs can be delayed while less urgent ones are being processed. Most urgent job first. This rule assigns an importance or urgency to each job and they are processed in order of decreasing urgency. The benefit of this rule is that more important jobs have higher priority, but this means that jobs with low priority can be stuck at the end of a queue for a long time. Shortest job first. A useful objective is to minimize the average time spent in the system, where time in the system equals processing time plus waiting time. If a patient needs 4 days treatment in a hospital but waits in the queue for 60 days, their time in the system is 64 days. Taking the jobs in order of increasing duration minimizes the average time spent in the system. This allows smaller jobs to move on quickly, but longer jobs can spend a long time waiting. Earliest date first. This sorts jobs into order of delivery date, and the ones that are due earliest are processed first. This has the benefit of minimizing the maximum lateness of jobs. When you have a set of jobs like this, the total time to do the work is fixed regardless of the order in which you take them, assuming the time to transfer from one job to the next is constant. But the order of doing jobs changes other measures of performance, and it is this that can be most important. Now let's see an example. A master schedule of ABC company shows that the following 6 jobs have to be done by a heavy lift crane. What would be a reasonable schedule for the crane? The simplest way of tackling this problem uses a decision rule like the 4 we mentioned. First come, first served. It gives the following schedule. The jobs are finished by day 52. Every sequence of jobs will give the same completion time, but they will perform differently when judged by other measures. Shortest first gives the following schedule. This minimizes the average time in the system, which is the same as the average finish time. Here this is 134 divided by 6, which is 22.3 days, compared with 190 divided by 6 or 31.7 days for first come first served. By day 36, this schedule has finished 5 jobs, while the previous schedule had only finished 3. Most urgent first. Here the company has used some notional scale of importance to give this schedule. Next one, in order of due date, gives the following schedule. This minimizes the maximum lateness. Here the maximum lateness is 4 days for jobs D and F, and an average lateness of 10 divided by 6 or 1.7 days. Whichever the company uses, they can use the results to schedule all activities and control the associated movements through supply chains. Now we will continue with master production schedule. At the conceptual level, the master production schedule translates the sales and operations plan of the company into a plan for producing specific products in the future. Where the sales and operations plan provides an aggregate statement of the manufacturing output required to reach company objectives, the master production schedule is a statement of the specific products that make up that output. The master production schedule is the translation of the sales and operations plan into producible products with their quantities and timing determined. On a day-to-day basis, the master production schedule provides the information by which sales and manufacturing are coordinated. Also, it shows when products will be available in the future, thereby providing the basis for sales to promise delivery to customers. These promises will be valid as long as manufacturing executes the master production schedule according to plan. When conditions arise that create customer promise dates that are unacceptable from a marketing or manufacturing perspective, the master production schedule provides the basis for making the required trade-offs. At operational level, the most basic concern is with the construction of the MPS record and updating it over time. This record is developed to be compatible with the material requirements planning system and to provide the information for coordinating with sales. Over time, as production is completed and products are used to meet customer requirements, the master production schedule record must be kept up to date. Doing this means implementing a periodic review and update cycle that we term rolling through time. Updating the record involves processing master production schedule transactions, maintaining the MPS record, responding to exception conditions, and measuring effectiveness on a routine basis. The master production schedule is a statement of planned future output. It specifies the products or product options that will be completed, the time of completion, and the quantities to be completed. It is the anticipated build schedule for the company. As such, it is a statement of production, not a statement of demand. The master production schedule specifies how product will be supplied to meet future demand. Let's stress the fact that the master production schedule is not a forecast, since manufacturing is held responsible for meeting the master production schedule requirements. Now let's continue with some master production schedule techniques. We will start with an example shown here, master production schedule example. It involves an item with a beginning on-hand inventory of 20 units, a sales forecast that is increasing each period, typically weekly, and a master production schedule of 10 units per each period. The master production schedule row states the timing for completion of units available to meet the demand. As with the sales and operations plan, the projected available balance is governed by the following relationship. It is found by beginning balance plus master production schedule minus the forecast. Data in this row show the expected condition as of the current period. The record covers a 5-period planning horizon for which the total sales forecast is 43 and the total master production schedule or planned production is 50 units. Many different approaches can be used to meet the demand. The strategy shown in this figure is a level strategy where production is held constant. There is another strategy we talked about in previous section, a chase strategy or some other type of mixed strategy that might be appropriate. The exact strategy chosen depends on characteristics of the process employed for making the item and the constraints within the company. The goal is to find the plan that best balances costs and benefits. Often the same production process is used to make different items. In this case, production must switch from one item to the next, and this switching usually involves some change over time. To minimize the impact of the loss of production due to the changeover, parts are made in batches rather than one at a time. The number of units made in a batch is referred to as the lot size. In the next figure, we show a master production schedule where the lot size has been set to 30 units. In addition, in this example, we have set a safety stock of 5 units. The safety stock provides a cushion to protect the schedule against uncertainty in demand. Safety stock in the context of master production scheduling is the additional inventory and capacity planned as protection against forecast errors and short-term changes in the backlog. Logically, we can think of the 5 units as a trigger level. When projected available balance falls below 5 units, a new batch of parts are scheduled for production. In this picture, if we did not produce another batch in period 3, inventory will drop to 2 units and would be below our safety stock level. Therefore, we schedule a lot of 30 units to be produced in period 3 to replenish inventory. Manufacturing using a lot size procedure produces inventories that last between production runs. This inventory, called cycle stock, is part of the projected available inventory row in the schedule. The larger the lot size, the greater the average cycle stock carried in the schedule. Let's continue. The master production schedule is a rolling schedule that requires updating the record, so the master production schedule reflects actual current conditions. The updating captures the impact of actual transactions that have occurred from one period to the next in the master production schedule. Here in this picture, we show the situation at the start of the second period, now for periods 2 through 6, using the original master production schedule for the 5-week period given in this figure. No material was received during the first week because none was planned by the master production schedule, but actual sales were 10 units instead of 5 units. So now we see that on-hand inventory at the beginning of period 2 is 10 units rather than the 15 we expected last period. The projected available balance reflects these changes and assumes that master schedule planned during period 1. Our forecast has also been updated, reflected an anticipated surge in demand in periods 2, 3, and 4. Note that we have added a forecast for period 6 as part of rolling our plan forward one period. The increase in demand has created some problems that we need to deal with in the master schedule. If possible, we would like to move up the batch currently scheduled for production in period 3 to period 2. This would keep us from stocking out in period 2. In addition, we need to schedule batches in periods 3 and 5. These changes were made using the same triggering logic used before, where we maintain a safety stock level of 5 units. The revision of this master schedule, shown here, solves the problem of projected available negative inventory, but puts in clear focus the question of feasibility. Does the company have the capacity to immediately produce a batch that was originally scheduled for period 3? Can the company produce batches in 2 consecutive periods in the future? Is material available to meet the requirements of this schedule? Moreover, high costs are typically associated with making production changes. The master production schedule should be buffered from overreaction with changes made only when essential. We will continue in the next lecture with some more techniques. Alright, let's continue with some other master production schedule techniques. Now we're going to talk about order promising and available to promise. For many products, customers do not expect immediate delivery but place orders for future delivery. The delivery date or promise date is negotiated through a cycle of order promising, where the customer either asks when the order can be shipped or specifies a desired shipment date. If the company has a backlog of orders for future shipments, the order promising task is to determine when the shipment can be made. Order promising can be coordinated with production schedule by using a concept known as available to promise. The first figure here builds on the lot-sized master production schedule from the previous lecture. The original sales forecast and master production schedule as of the beginning of week 1 are shown. In addition, we now consider an orders row that reflects shipments that are tied to actual customer orders. We now have data on expected shipments and consider this when planning the master schedule. Of course, this information could also be shared with the sales group so that they understand the precise implication of promising orders to customers on a particular date. The row labeled orders in this figure represents the company's backlog of orders at the start of the first period. 5 units are promised for shipment in the first period, 3 more in period 2, and additional 2 units promised for delivery in period 3. Thus, the cumulative order backlog is 10 units over those 3 periods. The logic for calculating available to promise will be explained now. But before this, let's consider the issues associated with the calculation. When we consider the situation as of the beginning of period 1, we have 20 units in inventory. And between now and when we expect to replenish our supply in period 3, we have orders for 8 units. So between now and the beginning of period 3, we could deliver an additional 12 units. We can ignore the issue of safety stock in this analysis because those units are available and could be sold if we can find customers for them. When we get to period 3, the whole cycle starts again. So far we only have orders for 2 units, so out of that second batch we could promise another 28 units for delivery in period 3 and out into the future. This logic we just described is usually known as discrete available to promise logic, where the first period and every order after it are considered independent from a planning point of view. We also could take cumulative available to promise view and carry the units that we can promise from one batch forward to the next. This is shown in this figure. The cumulative available to promise. Here is a step-by-step process explained for calculating the master production schedule, including available to promise calculations. So first we calculate projected available inventory, which equals to projected available inventory plus master production schedule minus the maximum between forecast and actual orders. We calculate this for every period in the planning horizon. Then, depending on the logic, if we have discrete logic, ATP calculations, for the first period, ATP is on hand inventory plus master production schedule minus sum of the orders until the next master production schedule. And for each period, when a subsequent master production schedule occurs, ATP is master production schedule minus sum of the orders until the next master production schedule. If we use ATP calculations and cumulative logic, as in the second example here, for the first period, ATP is on hand plus master production schedule minus sum of the orders until the next master production schedule. Therefore, for each period when a subsequent master production schedule occurs, available to promise is previous available to promise plus master production schedule minus sum of the orders until the next master production schedule. All those formulas are inserted here in those tables, so when you download the tables from the resources section of the lecture, you can use them and change the numbers to see how it works. One thing that we see in step 1 of the process is the calculation for projected available inventory. When calculating that, what we expect to have available in a period, we use the maximum of forecasts and actual orders. This reflects a conservative approach to the demand side of the equation. Our hope is that during a period we will eventually sell up to the forecast. And if this proves to be true, we want to reflect the additional sales in projecting our inventory balance. Some experts refer to this as consuming the forecast. Using our example in period 1, we see all 5 units of the forecast have been consumed. To illustrate this idea further, let's roll our plan to period 2, assuming that we delivered the 5 units scheduled in period 1. Let's consider a set of new orders that come in during period 2 and see if we can accept them, assuming they are received in the following sequence shown here. Now, here we show how things look prior to making any changes to our master schedule. Here the projected available balance reflects demand as the maximum of orders or forecast. As we can see, another batch needs to be scheduled in period 5. because sales were higher than expected and we would expect to stock out 6 periods from now. This figure here reflects the status of our master schedule after entering a new batch in period 5 and a second batch in period 6. Using the discrete ATP logic, it is a little difficult to understand how sound the schedule is given the positive ATP values in periods 2, 3 and 5 and the negative value in period 6. Cumulative ATP values shown in the next table show that the schedule looks fine. What works better in practice, discrete or cumulative ATP calculations, depend on the actual situation within the company. Even though the cumulative approach looks attractive with this example, in practice it might overstate the real availability in the future due to the timing of how orders are booked. Within software packages, there are often options for how these calculations are performed and for the format of the schedules. The use of both the projected available balance and the available to promise row is the key to effective master production schedule. Using available to promise to book orders means that it is unlikely that a customer promise will be made that cannot be kept. Note, this may mean some orders must be booked at the end of a planning horizon concurrent with creating an additional master production schedule order. As actual orders are booked and reflected in the order row or anticipated in the forecast row or shipped as reflected in a projected available balance, the available to promise row provides a signal for the creation of new master production schedule orders. Now let's see the master production schedule in assemble to order environment. The assemble to order form is typified by an almost limitless number of end item possibilities due to the myriad combinations of basic components and subassemblies. This means that the master production schedule unit in the assemble to order environment cannot feasibly be based on end items. The bill of materials specifies the ingredients required to make each part number or assembly in our system. It is a listing of all the subassemblies, intermediates, parts and raw materials that go into a parent assembly, showing the quantity of each required to make an assembly. The bill of material may also be called the formula, recipe or ingredients list in certain process industries. The assembled order form is unique in that a relatively few number of modular options can be combined to make a unique end item wanted by a customer. One approach that we could take to build the unique item that a customer wants would be to simply take the order and then construct the item totally from scratch. First building components, then assembling the components into the option modules, and finally assembling the options into the final product. Of course, this could take a considerable amount of time, and our customers may not be willing to wait that long. Another approach, one that would make customer response much quicker, would be to synchronize two parallel production systems. The first system is designed to efficiently produce the components and options that are needed in the final product, and the second system is a final assembly process that is designed to put together a product from the options selected by each customer. For this approach to be successful, these two systems must be tightly integrated so that the desired options are available when the customer orders the product. The two-level master production schedule, which we will discuss in the next lecture, is designed to support this type of integration. A special type of planning bill is one known as the super bill. The super bill describes the related options or modules that make up the average end item. For example, a maker of notebook computers may know from past experience that the average computer has 6 GB of memory, 0.5 web cameras, or half the notebooks are configured with a camera, 0.4 cell phone interface modems, and 0.7 extra high contrast displays. This end item is impossible to build, but it's very useful information for planning and master scheduling. Our super bill will show all the possible options as components with their average decimal usage. The super bill combines the modules or options with the decimal usage rates to describe the average notebook computer. The bill of material logic forces arithmetic consistency in the mutually exclusive options. For example, the sum of two possible display screens options needs to equal the total number of notebooks computers made. The super bill is as much a marketing tool as a manufacturing one. With it, instead of forecasting and controlling individual models, the forecast is now stated in terms of total average units, with attention given to percentage breakdowns, to the single-level super bill of materials, and to managing module inventories by using available to promise logic on a day-to-day basis as actual customer orders are booked. Now let's consider an artificially small example. The ABC companies makes tillers in the following options: horsepower 2, 3, and 4, drivetrain, chain, and gear, and brand name Max, Garden, and Original. The total number of end item buildable units is 18. Management and master scheduling at the end item level would mean each of these would have to be forecast. The figure here shows a super bill for 3 horsepower tillers. Using this artificial end item for an average 3 horsepower tiller, only one forecast is needed from marketing. More important, the master production schedule unit can be the super bill. The entry of 1000 3 horsepower super bill units into the master production schedule would plan the appropriate quantities of each of the options to build 1000 3 horsepower units in the average option proportions. Actual orders may not reflect the average in the short run. Here on the figure, we show the use of safety stocks for the options to absorb variations in the mix. No safety stock is shown for the common parts. This means protection is provided for products mix variances, but not for variances in the overall master production schedule quantity of 3 horsepower tillers. A commitment to a master production schedule quantity for the super bill means exactly that number of common parts will be needed. In this example, if 1000 3 horsepower super bills were entered, the bill of materials would call for 1000 common part modules, 600 gear options, 400 chain options, 400 max, 500 garden options, and 100 original options. The safety stocks allow shipments to customers to vary from the usages specified by the bill of materials percentages. Although 600 of the 1000 3 horsepower tillers are expected to be finished with the gear drive option, as many as 750 can be promised because of the safety stock. Similar flexibility exists for all other options. Safety stocks are maintained with MRP logic, so appropriate quantities are maintained as orders arrive. Matched sets occur because when one unit of the module is specified for safety stock, all parts required for that unit will be planned. Furthermore, costs of all safety stocks are readily visible. Marketing has the responsibility to optimize the mix and review safety stock levels. Order entry using planning bill of materials concept tends to be more complex than when the structure is end item based. To accept a customer order, the available to promise logic must be applied to each option in the order, meaning it's necessary to check each of the affected modules. This figure here shows the flow for a particular customer order, in this case for 25 max 3 horsepower units in the gear option. The safety stock are available for promising and will be maintained by material requirements planning as additional master production schedule quantities are planned. We can provide the information needed to implement the logic shown on this slide using a concept often known as a two-level master production schedule, which we will describe in the next lecture. Now let's explore how we can manage using a two-level master production schedule. When we use a planning bill of material, the final assembly schedule is often used to state the exact set of end products to be built over some time period. It is the schedule that serves to plan and control final assembly and test operations, including the launching of final assembly orders, picking of component parts, subassembly, painting, or other finishing. In short, the final assembly schedule controls that portion of the business from fabricated components to completed products ready for shipment. Many firms have found it is useful to coordinate the final assembly schedule and component production by using this concept known as two-level master production schedule. This technique is most useful for an assemble-to-order firm where it is critical that before an order is promised, key components are guaranteed to be available. The technique allows the use of available to promise logic at both the component level and at the final assembly level in the bill of materials. The typical situation has the firm using the super bill, such one that we showed the last lecture, and now we are going to use this super bill and we will explore a simple example and we will illustrate the idea using the Excel spreadsheet. Let's consider our ABC company and focus on two models of our 3 horsepower tillers, the branded Max and Original product. Let's assume that we plan to sell 100 units per week and that these will be assembled to order. We expect 40% of the demand to be the Max option and 10% to be Original. The other 50% are sold as options in other bundled products. These tables here shows the calculations for our two-level master schedule using discrete ATP logic. The first table, the 3 horsepower tillers, is the assembly plan for making our tillers. Here we see that we plan to make 100 tillers each period and that they will be assembled based on actual customer orders. We have already received 100 orders to be made in period 1, 72 in period 2, and 54 in period 3. As you can see, sales can take orders for 28 additional tillers in period 2, 46 in period 3, and 100 in period 4. Afterwards, using these discrete ATP calculations. The second part here is the master schedule for our max brand tour. We expect demand to be 40% of 3 horsepower tour demand. So we have 40 units each period. Our plan is to make to demand, but just to be safe, we want to carry 10 of these in inventory as safety stock. We have firm orders for 42 of these in period 1, 37 period 2, and 23 in period 3. We would like to assemble these in lot sizes of 80 at a time. In calculated projected available inventory, we use the rules that demand is the greater of actual orders and forecast demand, so the projected available balance for period 1 is 48 units. Here we have included the formulas, so we have 10 on hand plus 80 master production schedule minus 24 the actual demand, which is greater than the forecast. In period 2, projected available balance is 88, also using a formula. And note here that we had to schedule another 80 units in period 2 to keep our projected inventory level above the 10 unit safety stock level. So here we have used available to promise using discrete logic. For the first period, the calculation here is 48 units. Also, we have put the formula. We have 10 on hand, 80 master production schedule minus 42. For period 2, we have 20 using the same logic, and for period 4, when our next master production schedule is due, available to promise is calculated at 80 units. And here we have the table for 10% original 3 HP tours using absolutely the same logic and calculations. On this figure here, and these tables, we have calculated available to promise using cumulative logic. For this cumulative logic, as we saw in the previous lectures, unsold units are carried forward and included with our next master production schedule. Here also we have for 40% max 3 HP and 10% 3 HP tours. The logic for calculating available to promise is exactly the same as used previously. By doing this at these two levels, we are able to coordinate the sales of the various models with our actual assembly schedule. Overall, the two-level master production schedule approach helps us align the manufacturing planning and control process closely to market forces. Products are planned and controlled in the way they are sold as opposed to the way they are designed or manufactured. A stable master production schedule translates into stable component schedule, which means improved performance in plant operations. Too many changes in the master production schedule are costly in terms of reduced productivity. However, too few changes can lead to poor customer service level and increased inventory. The objective is to strike a balance where stability is monitored and managed. This figure here shows the first 8 weeks in the master production schedule as frozen. This means no changes inside of 8 weeks are possible. In reality, no may be a bit extreme. If the CEO dictates a change, it will probably happen, but such occurrences should be rare. Many firms do not use the term frozen, saying that anything is negotiable, but negotiations get tougher as we approach the present time. However, a frozen period provides a stable target for manufacturing to hit. Time fencing is an extension of the freeze concept. Many firms set time fences that specify periods in which various types of change can be handled. A common practice, for example, is to have 3 time fences, for example 8, 16, and 24 weeks. The marketing and logistics people could make any changes that they wanted beyond the 24-week fence as long as the sum of all master production schedule records is synchronized with the production plan. From weeks 16 to 24, substitutions of one end item for another would be permitted, provided required parts would be available and the production plan was not violated. From weeks 8 to 16, the master production schedule is quite rigid, but minor changes within the model series can be made if component parts are available. The period before 8 weeks is basically a freeze period, but occasional changes are made even within this period. To achieve the productivity necessary to remain competitive, stability in short-range manufacturing plans is essential. 2 common fences are the demand fence and the planning fence. The demand fence is the shorter of the 2. Inside the demand fence, the forecast is ignored in calculating the projected available balance. The theory is that customer orders, not the forecast, matter in the near term. The planning fence indicates the time at which the master production scheduler should be planning more master production schedule quantities. Within the demand fence, it is very difficult to change the master production schedule. Between the demand fence and the planning fence, management trade-offs must be made to make changes. Outside the planning fence, changes can be made by the master production scheduler only. For companies assembling end items from components produced in batch manufacturing processes, material requirements planning is central to the development of detailed plans for part needs. It is often where companies start in developing their manufacturing planning and control systems. Facility with time-phased planning and the associated time-phased records is basic to understanding many other aspects of the manufacturing planning and control system. For companies using MRP, the General Manufacturing Planning and Control Framework is shown in this picture and shows that detailed requirements planning is characterized by the use of time-phased, period-by-period requirement records. Several other supporting activities are shown in the front end, engine and back end of the system as well. The front end of the manufacturing planning and control system produces the master production schedule. The back end or execution system deals with production scheduling and control of the factory and with managing materials coming from vendor plants. The detailed material planning function represents a central system in the engine portion here. For firms preparing detailed materials plans using MRP, this means taking a time-phased set of master production schedule requirements and producing a resultant time-phased set of component parts and raw material requirements. In addition to master production schedule inputs, MRP requires 2 other basic inputs. A bill of material shows for each part number what other part numbers are required as direct components. For example, for a car, it could show 5 wheels required, 4 plus the spare. For each wheel, the bill of material could be a hub, tire, valve stem, and so on. The second basic input to MRP is inventory status. To know how many wheels to make for a given number of cars, we must know how many are on hand, how many of those are already allocated to existing needs, and how many have already been ordered. An MRP system serves a central role in material planning and control. It translates the overall plans for production into the detailed individual steps necessary to accomplish those plans. It provides information for developing capacity plans, and it links to the systems that actually get the production accomplished. In this and next couple of lectures, we are going to examine several aspects of record processing. And in this one, we will start with basic material requirements planning record. At the heart of the manufacturing planning and control system is a universal representation of the status and plans for any single item or part number, whether raw material, component part, or finished good. The MRP time-phased record. This figure here displays that type of record and shows the following information. Let's examine the figure. Gross requirements is the anticipated future usage of or demand for the item during each period. Scheduled receipts, existing replenishment orders for the item due in at the beginning of each period. Projected available balance, the current and projected inventory status for the item at the end of each period. And plant order releases, plant replenishment orders for the item at the beginning of each period. The top row in the figure indicates periods that can vary in length from a day to a quarter or even longer. This period is also called a time bucket. A widely used time bucket or period is 1 week. A timing convention is that the current time is the beginning of the first period. The initial available balance of 4 units is shown prior to period 1. The number of periods in the record is called the planning horizon. In this simple example, the planning horizon is 5 periods. The planning horizon indicates the number of future periods for which plans are made. The second row, gross requirements, is the anticipated future usage of the item or demand for the item. The gross requirements are time-phased, which means they are stated on a unique period-by-period basis rather than aggregated or averaged. Gross requirements here are stated as 10 units in period 2, 40 in period 4, and 10 in period 5, rather than as a total requirement of 60 or as an average requirement of 12 per period. This method of presentation allows for special orders, seasonality, and periods of no anticipated usage to be explicitly taken into account. A gross requirement in a particular period will be unsatisfied unless the item is available during that period. Availability is achieved by having the item in inventory or by receiving either a scheduled receipt or a planned replenishment order in time to satisfy the gross requirement. Another timing convention comes from the question of availability. The item must be available at the beginning of the time bucket in which it is required. This means plans must be so made that any replenishment order will be in inventory at the beginning of the period in which the gross requirement for that order occurs. The scheduled receipts row describes the status of all open orders, work in process, or existing replenishment orders for the item. This row shows the quantities ordered and when we expect these orders to be completed. Scheduled receipts result from previously made ordering decisions and represent a source of the item to meet gross requirements. For example, the gross requirements of 10 in period 2 cannot be satisfied by the 4 units presently available. The scheduled receipts of 50 due in period 1 will satisfy the gross requirements in period 2 if things go according to the plan. Scheduled receipts represent a commitment. For an order in the factory, necessary materials have been committed to the order, and capacity at work centers will be required to complete it. For a purchased item, similar commitments have been made to a vendor. The timing convention used for showing scheduled receipts is also at the beginning of the period. The order is shown in the period during which the item will be available to satisfy a gross requirement. The next row is projected available balance. The time convention in this row is the end of the period. The row is the projected balance after replenishment orders have been received and gross requirements have been satisfied. For this reason, the projected available balance row has an extra time bucket shown at the beginning. It shows the balance at the present time. So in this example, the beginning available balance is 4 units. The quantity shown in period 1 is the projected available balance at the end of period 1. The projected available balance shown at the end of a period is available to meet gross requirements in the next and succeeding periods. For example, here the 54 units shown as the projected available balance at the end of period 1 result from adding the 50 units scheduled to be received to the beginning balance of 4 units. The gross requirement of 10 units in period 2 reduces the projected available balance to 44 units at the end of period 2. Here we use the term projected available balance instead of projected on hand balance for a very specific reason. Units of the item might be on hand physically but not available to meet gross requirements because they are already promised or allocated for some other purpose. The planned order releases row is determined directly from the projected available balance row. Whenever the projected available balance shows a quantity insufficient to satisfy gross requirements, negative quantity, additional material must be planned for. This is done by creating a planned order release in time to keep the projected available balance from becoming negative. For example, here the projected available balance at the end of period 4 is 4 units. This is not sufficient to meet the gross requirement of 10 units in period 5. Because the lead time is 1 week, the MRP system creates a planned order at the beginning of week 4, providing a lead time offset of 1 week. Since we have used a lot size of 50 units, the projected available balance at the end of week 5 is 44. Another way that this logic is explained is to note that the balance for the end of period 4, 4 units, is the beginning inventory for period 5, during which there is a gross requirement of 10 units. The difference between the available inventory of 4 and the gross requirement of 10 is a net requirement of 6 units in period 5. In this way, an order for at least 6 units must be planned for period 4 to avoid a shortage in period 5. The MRP system produces the planned order release data in response to the gross requirement, scheduled receipt, and projected available data. When a planned order is created for the most immediate or current period, it is in the action bucket. A quantity in the action bucket means some action is needed now to avoid a future problem. The action is to release the order, which converts it to a scheduled receipt. The planned order releases are not shown in the scheduled receipt row because they haven't yet been released for production or purchasing. This basic MRP record we just described provides the correct information on each part in the system. Linking these single part records together is essential in managing all the parts needed for a complex product or customer order. Key elements for linking the records are the bill of materials, the explosion process using inventory and scheduled receipt information, and lead time offsetting. We're going to explain all those in the next couple of lectures. Now let's see some simple examples of bill of materials and different types of diagrams. The first slide shows a snow shovel and item part number 1605. The complete snow shovel is assembled using 4 rivets and 2 nails from the top handle assembly, scoop assembly, scoop, shaft connector, and shaft. The top handle assembly in turn is created by combining the welded top handle bracket assembly with the wooden handle using 2 nails. The welded top handle bracket assembly is created by welding the top handle coupling to the top handle bracket. In a similar way, the scoop assembly combines the aluminum scoop with the steel blade using 6 rivets. Explaining even this simple assembly process is a hard task. Moreover, such diagrams as this one get more complicated as the number of sub-assemblies, components and parts used increases, or as they are used in increasingly more places. There are 2 techniques that get at this problem nicely. These are the product structure diagram, shown here, and indented bill of materials, shown on this slide. Both of them provide the detailed information shown on the first slide, but the indented bill of material has the added advantage of being easily printed. We can see that both the product structure diagram and the indented bill of material show exactly what goes into what instead of being just a parts list. For example, to make 113-122 top handle assembly, we see by the product structure diagram that 457 top handle, 2082 nails, and 495 bracket assembly are needed. And the same information is shown in the intended bill of material. Here we see that the 3 required parts are indented and shown 1 level beneath the 13122 top handle. Note also that we don't need a top handle bracket 129 or a top handle coupling 1118 to produce a top handle assembly. These are only needed to produce a bracket assembly 11495. In essence, the top handle assembly does not care how a bracket assembly is made, only that it is made. Making the bracket assembly is a separate problem. Let's continue our discussion related to records processing with gross to net explosion. Explosion is the process of translating product requirements into component part requirements, taking existing inventories and scheduled receipts into account. Explosion may be viewed as the process of determining for any part number the quantities of all components needed to satisfy its requirements. and continuing this process for every part number until all purchased and or raw material requirements are exactly calculated. As explosion takes place, only the component part requirements, net of any inventory or scheduled receipts, are considered. In this way, only the necessary requirements are linked through the system. Although this may seem like an obvious goal, the product structure can make a determination of net requirements more difficult than it seems. Let's illustrate this by the snow shovel example from the previous lecture. Suppose that the company wants to produce 100 snow shovels, and we are responsible for making the 13 1 to 2 top handle assembly. In this picture here, we are given current inventory and scheduled receipts information, from which the gross requirements and net requirements for each component of the top handle can be calculated. The gross and net requirements in the figure may not correspond to what we feel they should be. It might at the outset seem that since one top handle coupling, 1118, is used per shovel, the gross requirements should be 100 and the net requirements 46, instead of the 48 and 0 shown here. To produce 100 shovels means we need 100 top handle assemblies, part 13, 1 to 2. 25 of these 100 can come from inventory, resulting in a net requirement of 75. As we need to make only 75 top handle assemblies, we need 75 top handles and bracket assemblies. These 75 is the gross requirements for parts 4, 5, 7 and 11495, which is indicated by the colored numbers in the picture in red. Because 2 nails part 082 are used per top handle assembly, the gross requirement for 082 is 150. The 25 units of top handle assembly inventory contains some implicit inventories of handles, brackets and nails, which the gross to net process takes into account. Looking on down, we see that there are 27 units of the bracket assembly in inventory, so the net requirement is for 48. This becomes the gross requirement for the bracket and coupling. Since there are 39 handle couplings in inventory and 15 scheduled for receipts, there is no net requirements for part 1118. Gross to net explosion is a key element of MRP systems. It not only provides the basis for calculating the appropriate quantities, but also serves as the communication link between part numbers. It is the basis for the concept of dependent demand. The demand or gross requirements for top handles depends on the net requirements for top handle assemblies. To correctly do the calculations, the bill of material, inventory, and scheduled receipt data are all needed. With this data, the dependent demand can be exactly calculated. It doesn't need to be forecast. On the other hand, some independent demand items, such as the snow shovel, are subject to demand from outside the company. The need for snow shovels will have to be forecast. The concept of dependent demand is often called the fundamental principle of material requirements planning. It provides the way to remove uncertainty from the requirement calculations. Gross to net explosion, explained in the previous lecture, tells us how many of each subassembly and component parts are needed to support a desired finished product quantity. What it doesn't do, however, is tell us when each component and subassembly is needed. From the example of snow shovel, clearly the top handle bracket and top handle coupling need to be welded together before the wooden top handle is attached. These relationships are known as precedent relationships. They indicate the order in which things must be done. In addition to precedent relationships, determining when to schedule each component part also depends on how long it takes to produce the part, or this is the lead time. Despite the need to take lead time differences into account, many systems for component parts manufacturing ignore them. For example, most furniture manufacturers base production on what is called a cutting. In the cutting approach, if a lot of 100 chairs were to be assembled, then 100 of each part with appropriate multiples are started at the same time. This figure is a Gantt chart, time-oriented bar chart, showing how this cutting approach would be applied to the snow shovel example. Also note that here processing times are also shown. This figure shows clearly that the cutting approach, which starts all parts as soon as possible, will lead to unnecessary work in process inventory. For example, the top handle bracket 129 doesn't need to be started until the end of day 9, since it must wait for the coupling 1118 before it can be put into its assembly 11495, and part 1118 takes 10 days. In the cutting approach, parts are scheduled earlier than needed to be. This results from using front schedule logic, scheduling as early as possible. What should be done is to back schedule, start each item as late as possible. And this is a back schedule for our example. The schedules for parts 1118, 11495, 13122 and 1605 don't change since they form a critical path. All of the other parts, however, are scheduled later in this approach than in the front scheduling approach. A substantial savings in work in process inventory is obtained by this shift of dates. Backscheduling has several obvious advantages. It will reduce work in process, postpone the commitment of raw materials to specific products, and minimize storage time of completed components. Implementing the backschedule approach, however, requires a system. The system must have accurate bill of materials data and lead time estimates, some way to ensure all component parts are started at the right times, and some means of tracking components and subassemblies to make sure they are all completed according to plans. The cutting approach is much simpler since all component parts are started at the same time and left in the pipeline until needed. MRP achieves the benefits of the backscheduling approach and performs the gross to net explosion. In fact, the combination of schedules and gross to net explosion is the heart of MRP. Now let's continue with linking the MRP records. This spreadsheet shows the linked set of individual time-phased MRP records for the top handle assembly of the snow shovel. We already used the first 5 periods of the 082 or nails shown here as the record in the lecture 2. To see how this fits into the whole, we start with the snow shovels themselves. We said that 100 snow shovels were going to be made, and now we see the timing. That is the gross requirement row in the MRP record for part number 13122, which shows the total need of 100 time-phased as 20 in week 2, 10 in week 4, 20 week 6, 5 week 7, 35 week 9, and 10 in week 10. Because each snow shovel takes a top handle assembly, the gross requirements row for the top handle assembly shows when shovel assembly is to begin. Note that total plant orders for the top handle assembly is the net requirement of 75 that we calculated before in the gross to net calculations in the previous lecture. It is here 75. The lead time for the top handle assembly is 2 weeks, calculated as the 5 days processing time plus 5 days for paperwork. The lead time for each of the other records is similarly calculated. 1 week or 5 days of paperwork time is added to the processing time and the total rounded to the nearest 5-day week. The current inventories and scheduled receipts for each parts are also those shown in the previous lecture. The scheduled receipts are shown in the appropriate periods using the 2-week lead time and recognizing a net requirement of 5 units in week 4 for the top handle assembly. We see the need to plan an order for week 2 of 5 units. The plant order release of 5 units in week 2 become a gross requirement in week 2 for the top handles as shown by the circles and arrow in this spreadsheet. Note also that the gross requirements for the nails and brackets in period 2 derive from this same plant order release with 2 nails per top handle assembly. So here you can see brackets and nails. Thus the communication between records is the dependent demand that we saw illustrated before in the gross to net calculations in the previous lectures. The remaining plant order release for top handle assembly exactly meet the net requirements in the remaining periods offset for the lead time. The ordering policy used for these items is called lot-for-lot sizing. An exception to the lot-for-lot procedure is the ordering of nails, which is done in lots of 50. In the case of the nails, the total plant orders will not necessarily add up to the net requirements. Another part for which there is a discrepancy between the plant order and the net requirements calculated in the previous lecture is the top handle coupling. For this part, a safety stock of 20 units is desired. This means the plant order logic will schedule a plant order release to prevent the projected available balance from going below the safety stock level. For the top handle couplings, this means a total of 4 units must be planned for period 2 and 10 for period 3 to maintain the 20 unit safety stock. The one element we have yet to clearly show is the back scheduling effect. We saw in the previous lectures that it would be desirable to delay the start of the top handle bracket, part 1 to 9, so that this item is completed at the same time as the top handle coupling, part 11-18. The MRP record showed that the start of the first plant order for part 129 isn't until week 4, 2 weeks after the first plant order for part 11-18. Both of these plant orders are to satisfy a gross requirement of 35 derived from the plant order for the bracket assembly in week 5. We see then that the orders are back-scheduled. This relationship can be more complicated than in our example, because the plant order release timing depends on the safety stock and inventory levels, as well as the lead times. The MRP system, however, coordinates all of the information and determines the appropriate plant order release dates based on back scheduling. At this point, we see fully the linking of the MRP time-phased records. The plant order release row for the top handle assembly, this one, becomes with the appropriate multiplier the gross requirements row for each of its components: top handle, nails, and bracket assembly, and they are linked together. Once all the gross requirements data are available for a particular record, the individual record processing logic is applied and the plant order releases for the part are passed down as gross requirements to its components, following the product structure on a level-by-level basis. In some cases, parts will receive their requirements from more than one source, for example common parts, as it is true for the nails and rivets in this example. In these cases, gross requirements will reflect needs from more than one plant order release source. Again, the system accounts for this and incorporates it into the gross to net logic. Alright, so now let's continue with some system design considerations in this and the following lecture. We'll start with lot sizing. In the example we used in the previous lectures, we use a fixed lot size 50 units for the nails and the lot for lot procedure. The lot size of 50 for the nails could have been someone's estimate of a good lot size or the result of calculation. The time-phased information can be used in combination with other data to develop lot sizes conforming to organizational needs. We might reach a conclusion for the top handle 1118 that it's undesirable to set up the equipment for 4 parts in week 2 and again for 10 parts in week 3. So we would combine the two orders. The time-phased record permits us to develop such discrete lot sizes that will exactly satisfy the net requirements for one or more periods. Several formal procedures have been developed for lot sizing the time-phased requirements. The basic trade-off usually involves elimination of one or more setups at the expense of carrying inventory longer. In many cases, discrete lot sizes possible with MRP are more appealing than fixed lot sizes. Compare here the residual inventory of nails in week 10 with that of the bracket assemblies, for example. At first glance, the lot for lot technique seems a bit too simple-minded since it does not consider any of the economic trade-offs or physical factors. However, batching plant orders at one level will increase gross requirements at the next level in the product structure. So, larger lot sizing near the end item level of the bill of materials cascades down through all levels. This in turn out that lot for lot is better than we might expect in actual practice, particularly at the intermediate levels in the bill of materials. This is especially the case when a product structure has many levels and the cascading effect becomes greatly magnified. This cascading effect can be mitigated to some extent for components and raw materials that are very common. When this is the case, again lot sizing may be appropriate. As a consequence, many companies employ lot sizing primarily at the end item and basic component levels, while intermediate subassemblies are planned on a lot-for-lot basis. Carrying out detailed component plans is sometimes facilitated by including safety stocks and/or safety lead times in the MRP records. Safety stock is a buffer of stock above and beyond that needed to satisfy the gross requirements. The picture illustrates this by incorporating safety stock for the top handle coupling. Safety lead time is a procedure whereby shop orders or purchase orders are released and scheduled to arrive one or more periods before necessary to satisfy the gross requirements. Safety stocks can be incorporated into MRP time-phased records. The result is that the projected available balance doesn't fall below the safety stock level instead of reaching zero. To incorporate safety lead time, orders are issued earlier and are scheduled to be received into inventory before the time that the MRP logic would indicate as necessary. This figure here shows the top handle bracket being planned with a 1 week safety lead time. Notice here that both the plant release and plant receipt dates are changed. Safety lead time is not just inflated lead time. Both safety stock and safety lead time are used in practice and can be used simultaneously. However, both are hedges indicating that orders should be released, launched, or that they need to be received when in fact this is not strictly true. To use safety stocks and safety lead times effectively, we must understand the technique's influence on plans. If they are not well understood, wrong orders can be sent to the factory, meaning workers will try to get out part A because of safety lead time or safety stock, when in fact part B would be required to meet a customer order. Safety stock tends to be used in MRP systems where uncertainty about quantities is the problem. For example, where some small amount of scrap, spare part demand, or other unplanned usage is a frequent occurrence. Safety lead time, on the other hand, tends to be used when the major uncertainty is the timing rather than the quantity. For example, if a firm buys from a vendor who often misses delivery dates, safety lead time may provide better results than safety stock. Low-level coding. If we see once again this picture, we see that the rivet part 14.1-7 is a common part. The plant order row for completed shovels will be passed down as gross requirements to the rivet. But there are additional requirements for the rivets from the scoop assembly 3.14. If we process the time-phased record for this common part before all of its gross requirements have been accumulated, the computations must be redone. The way this problem is handled is to assign low-level code numbers to each part in the product structure or the intended bill of material. By convention, the top final assembly level is denoted as level 0. In our example, the snow shovel would have a low-level code of 0. All immediate component parts, part numbers of this part, in this case 13.122, 048, 118, 062, 14.127, and 3.14, the scoop, are given the low-level code number 1. The next level down are level coded 2. And note that the common part rivet has just been recoded as level 2, indicating it is used lower in the product structure. The higher the level codes, the lower in the product structure the part is used. Consequently, the last level code assigned to a part indicates the lowest level of usage and is the level code retained for that part. We finish the example when
the part numbers 1 to 9 and 11-18 are coded level 3. The level code assigned to any part number is based on the part's usage in all products manufactured by a company. Once low-level codes are established, MRP record processing proceeds from one level code to the next, starting at level code 0. This ensures all gross requirements have been passed down to a part before its MRP record is processed. The result is planning of component parts coordinated with the needs of all higher-level part numbers. Within a level, the MRP record processing is typically done in part number sequence. Pegging relates all the gross requirements for a part to all plant order releases or other sources of demand that created the requirement. The pegging records contain the specific part number or numbers of the sources of all gross requirements. At level 0, for example, pegging records might contain the specific customer order to be satisfied by the gross requirements in the end item time-phased records. For lower level part numbers, the gross requirements are most often pegged to plant orders of higher level items, but might also be pegged to customer orders if the part is sold as a service part. Let's continue with some design considerations. Firm plant orders. The logic used to illustrate the construction of an MRP record for an individual part number is automatically applied for every processed part number. The result is a series of plant order releases for each part number. If changes have taken place since the last time the record was processed, plant order releases can be very different from one record processing cycle to the next. Because plant orders are passed down as gross requirements to the next level, the differences can cascade throughout the product structure. One device for preventing this cascading down through the product structure is to create a firm plant order. Firm plant order is a plant order that the MRP system does not automatically change when conditions change. To change either the quantity or timing of a firm plant order, managerial action is required. This means the trade-offs in making the change can be evaluated before authorization. The firm plant order provides a means for temporarily overriding the system to provide stability or to solve problems. For example, if changes are coming about because of scrap losses on open orders, the possibility of absorbing those variations with safety stock can be evaluated. If more rapid delivery of raw material than usual is requested to meet a special need, lead time can be reduced for that one order. An FPO means the system will not use the normal lead time offset from the net requirement for that order. Service parts. Service part demand must be included in the MRP record if the material requirements are not to be understated. The service part demand is typically based on a forecast and is added directly into the gross requirements for the part. From the MRP system point of view, the service part demand is simply another source of gross requirements for a part, and the sources of all gross requirements are maintained through pegging records. The low-level code for a part used exclusively for service would be 0. If it's used as a component part as well, the low-level code would be determined the same way as for any other part. As actual service part needs occur, it's to be expected that demand variations will arise. These can be partially buffered with safety stocks or by creative use of the MRP system. By careful examination of pegging records, expected shortage conditions for manufacturing part requirements can sometimes be satisfied from available service parts. Conversely, critical service part requirements can perhaps be met with orders destined for higher level items. Planning horizon. In this figure, the first planned order for top handle assemblies occurs in week 2. To meet period 4's gross requirement of 10 units. This planned order of 5 units in week 2 results in a corresponding gross requirement in that week for the bracket assembly, part 11495. This gross requirement is satisfied from the existing inventory of that part. But a different circumstance occurs if we trace the gross requirements for 35 top handle assemblies in week 9. The net requirement for 35 units in week 9 becomes a planned order release in week 7. This in turn becomes a gross requirement for 35 bracket assemblies, part 11495, in week 7 and a planned order release in week 5. This passes down to the top handle coupling, part 1118, which creates a planned order release for 4 units in week 2. This means the cumulative lead time for the top handle assembly is 7 weeks, from release of the coupling order in week 2 to receipt of the top handle assemblies in week 9. Schedule receipts and planned order releases. A true understanding of MRP requires knowledge of certain key differences between a scheduled receipt and a planned order. We noted such difference before. The scheduled receipt represents a commitment, whereas the planned order is only a plan. The former is much more difficult to change than the latter. A scheduled receipt for a purchased item means a purchase order, which is a formal commitment, has been prepared. Similarly, a scheduled receipt for a manufactured item means there is an open shop order. Raw materials and component parts have already been specifically committed to that order and are no longer available for other needs. One major result of this distinction is that planned order releases explode to gross requirements for components, but scheduled receipts, the open orders, do not. A related issue is seen from the following questions. Where would the scheduled receipt for the top handle assembly, part 13122, of 20 units in week 2, be reflected in the records for the component parts 457, 082, and 11495? The answer is nowhere. Scheduled receipts are not reflected in the current records for component parts. For that scheduled receipts to exist, the component parts would have already been assigned to the shop order representing the scheduled receipt for part 13122 and removed from the available balances of the components. As far as MRP is concerned, the 20 part 457, 40 part 082, and 40 and 20 part 11495 don't exist. They are on their way to becoming 20 part 13122. The 13122 record controls this process, not the component records. Let's now continue with some transaction processing and see how the MRP planners or planning activities can deal with change. To illustrate transaction processing issues, we use a simple example for one part. Here we see an MRP record for part A produced over the weekend preceding week 1. The planner for part A would receive this MRP record on Monday of week 1. The planner's first action would be to try to launch the plant order of 50 units in period 1. The manufacturing planning and control system would first check availability of the raw materials for this part and then issue an order to the shop to make 50, if enough raw material is available. Launching would require allocating the necessary raw materials to the shop order, removing the 50 from the plant order release row for part A, and creating a scheduled receipt for 50 in week 3 when they are needed. Thereafter, a pick ticket would be sent to the raw material area and work could begin. Let's assume during the week 1 the following changes occurred and the transactions were processed. Actual disbursement from stock for item A during week 1 were only 20 instead of the planned 30. The scheduled receipt for 50 during week 1 was received on Tuesday, but 10 units were rejected, so only 40 were actually received into inventory. The inventory was counted on Thursday and 20 additional pieces were found. The requirement date for the 45 pieces in week 5 was changed to week 4. Marketing requested an additional 5 pieces for samples in week 2, and the requirement for week 6 has been set at 25. The resultant MRP record produced over the weekend preceding week 2 is shown in this table. This MRP record illustrates two important activities of MRP planners. First, indicating the sources of problems that will occur as a result of database changes. And second, suggesting actions to ensure the system is telling the truth. Note the scheduled receipts presently due in week 3 here is not needed until week 4. The net result of all the changes to the database means it's now scheduled with the wrong due date, and the due date should be changed to week 4. If the change is not made, the job may be worked on ahead of some other job that is really needed earlier, thereby causing problems. So far we illustrated system dynamics by using a single MRP record. However, an action required on the part of an MRP planner may have been caused by a very complex set of database transactions involving several levels in the bill of materials. As an example, consider the MRP record shown here, which include 3 levels in the product structure. We have part C is used as a component in both parts A and B. Part C in turn is made from parts X and Y. The arrows in the figure depict the pegging data. The part C MRP record is correctly stated at the beginning of week 1. That is, no exception messages would be produced at this time. In particular, the 2 scheduled receipts of 95 and 91 respectively are scheduled correctly. Since delaying either by 1 week would cause a shortage and neither has to be expedited to cover any projected shortage. While the 2 scheduled receipts for Part C are currently scheduled correctly, transactions involving Part A and B can have an impact on the proper due dates for these open orders. For example, suppose an inventory count adjustment for Part A resulted in a change in the 30-unit plant order release from week 1 to week 3. In this case, the 95 units of Part C would not be needed until week 3, necessitating a reschedule. Similarly, any change in timing for the plant order release of 25 units of Part A in week 4 would call for a reschedule of the due date for 91 units of Part C. And finally, suppose a transaction requiring 75 additional units of Part B in week 5 were processed. This would result in an immediate release of an order for 100 units of Part C. This might necessitate rescheduling for Parts X and Y. The point here is that actions required on the part of an MRP planner can occur because of a complex set of database transactions involving many different parts. They may not necessarily directly involve the particular part being given attention by the MRP planner. The MRP system converts the master production schedule into a time-phased schedule for all intermediate assemblies and component parts. Detailed schedules consist of two parts: scheduled receipts or open orders and plant orders. Each scheduled receipt's quantity and timing or due date have been determined prior to release to the shop. We determine quantities and timings for plant orders through MRP logic using the inventory position, the gross requirements data, and specific procedures for making the decisions. A number of quantity determination, lot sizing procedures have been developed for determining order quantities in MRP systems, ranging from ordering as required, lot for lot, to simple decision rules, and finally to extensive optimizing procedures. The primary consideration in the development of lot sizing procedures for MRP is the nature of the net requirements data. The demand dependency relationship from the product structures and the time-phased gross requirements mean the net requirements for an item might appear as shown in this picture. First, it is important to note that the requirements do not reflect the key independent demand assumption of a constant uniform demand. Second, the requirements are discrete, since they are stated on a period-by-period basis, time-phased, rather than as a rate. And finally, the requirements can be lumpy, that is, they can vary substantially from period to period and even have periods with no requirements. Because MRP systems normally replan on a daily or weekly basis, timing affects the assumptions commonly made in using MRP lot sizing procedures. Here are the assumptions. First, since we aggregate component requirements by time period for planning purposes, we assume all requirements for each period must be available at the beginning of the period. Second, we assume all requirements for future periods must be met and can't be backordered. Third, since the system is operated on a periodic basis, we assume ordering decisions occur at regular time intervals. Next, we assume the requirements are properly offset for manufacturing lead times. And finally, we assume component requirements are satisfied at a uniform rate during each period. Therefore, we use average inventory levels in computing inventory carrying costs. In this and next lectures, we will illustrate the results from applying three different ordering procedures to the example data from the previous slide. And with this example, we will illustrate how these procedures vary in their assumptions and how much they utilize available data in making lot sizing decisions. Because of its simplicity, people often use the economic order quantity formula as a decision rule for placing orders in a requirement planning system. As the following example will show, however, the EOQ model frequently must be modified in requirements planning system applications. Because we base the EOQ on the assumption of constant uniform demand, the resulting total cost expression won't necessarily be valid for requirements planning applications. This table shows the results of ordering material in economic lot sizes for the data. In this example, the EOQ formula used average weekly demand of 92.1 units for the entire requirement schedule to compute the economic lot size. Note two order quantities are shown when received, and average inventory for each period was used in computing the inventory carrying costs. This example illustrates several problems with using economic lot sizes. When the requirements aren't equal from period to period, as it is often the case in MRP, fixed EOQ lot sizes result in a mismatch between order quantities and requirement values. This can mean excess inventory must be carried forward from week to week. As an example, 41 units are carried over into week 6 when a new order is received. In addition, we must increase the order quantity in those periods where the requirements exceed the economic lot size plus the amount of inventory carried over into the period. An example occurs in week 7. This modification is clearly preferable to the alternative of placing orders earlier to meet demand in such periods, since this would only increase inventory carrying costs. Likewise, the alternative of placing multiple orders in a given period would needlessly increase the ordering cost. And finally, use of the average weekly requirements figure in computing economic lot size ignores much of the information of the other information in the requirement schedule. This information concerns magnitude of demand. For instance, there appear to be two levels of component demand in this example. The first covers weeks 1 to 4 and 10 to 12. The second covers weeks 5 to 9. We could compute an economic lot size for each of these time intervals and place orders accordingly. This idea, however, would be difficult to implement because determining different demand levels requires a very complex decision rule. Please note that you can download all the spreadsheets used in the lectures from the downloadable resource section of the lectures, and also they're populated with formulas, so you can use them, just change the numbers, and you can use them using your numbers, and you can play around. Let's continue with another technique, period order quantities. And this is one way to reduce the high inventory carrying costs associated with fixed lot sizes, is to use the EOQ formula to compute an economic time between orders. We do this by dividing the EOQ by the mean demand rate. In this example, the economic time interval is approximately 2 weeks. The procedure then calls for ordering exactly the requirements for a 2-week interval. This is called the periodic order quantity. Applying this procedure to the data in our example, we achieve this picture. Also, you can see that the total costs are much lower, and this is because of the lower inventory or carrying costs. So the result actually is the same number of orders as the EOQ produces, but with lot sizes ranging from 20 to 250 units. Here. Consequently, inventory carrying cost has been reduced by 30%, thereby improving the total cost of the 12-week requirement schedule by 9% in comparison with the preceding EOQ result. Although the periodic order quantity procedure improves inventory cost performance by allowing lot sizes to vary, like the EOQ procedure, it too ignores much of the information in the requirement schedule. Replenishment orders are constrained to occur at fixed time intervals, thereby ruling out the possibility of combining orders during periods of light product demand, for example, during weeks 1 through 4. If, for example, orders placed in weeks 1 and 3 were combined and a single order were placed in week 1 for 55 units, combined costs can be further reduced by $160 or 4%. There is another procedure we are going to explore here, the part period balancing, which uses all the information provided by the requirement schedule. In determining an order's lot size, this procedure tries to equate the total costs of placing orders and carrying inventory. We will illustrate this point by considering the alternative lot size choices available at the beginning of week 1. This includes placing an order covering the requirements for week 1 only, then week 1 and 2, week 1, 2, 3, 1, 2, 3, 4, and so on. Inventory carrying costs for these 5 alternatives are shown right here. So here it is formula used, and we base these calculations on average inventory per period. That means the 1/2 average for 1 week, then 3 seconds on 1 week plus the average for the second week, and so on. Here you can see the formulas are inputted for you. When we calculate all those inventory carrying costs, we see that in this case the inventory carrying cost for alternative 4 here, alternative 4, ordering 55 units to cover demand for the first 4 weeks, most nearly approximates the $300 ordering cost. That is, alternative 4 balances the cost of carrying inventory with the ordering cost. Therefore, we should place an order at the beginning of the first week, and the next ordering decision need to be made until the beginning of week 5. When we apply these procedures to all the example data, we get the results shown in this table. As seen, total inventory cost falls almost with $500. Here we have 3,945 and here 3,485, or it's 13% lower than the cost obtained with the periodic order quantity procedure. The part period balancing procedure permits both lot size and time between orders to vary. Thus, for example, in periods of low requirements, it yields smaller lot sizes and longer time intervals between orders than occur in high demand periods. This results in lower inventory-related costs. Despite the fact that part period balancing utilizes all available information, it won't always yield the minimum cost ordering plan. Although this procedure can produce low-cost plans, it may miss the minimum cost since it doesn't evaluate all possibilities for ordering material to satisfy demand in each week of the requirements schedule. Now let's continue with some buffering concepts, safety stock and safety lead time. So let's just make clear that buffering is not the way to make up for a poorly operating MRP system. First, categories of uncertainties. There are two basic sources of uncertainty affect an MRP system: demand and supply. These are further separated into two types: quantity uncertainty and timing uncertainty. The combination of sources and types provides the four categories of uncertainty illustrated in this picture. Demand timing uncertainty is illustrated by timing changes in the requirements from period to period. For example, the projected requirements for 372 units in period 7 actually occurred in period 4. The shift might result from a change in the promise date to a customer or from a change in a plant order for a higher level item on which this item is used. Supply timing uncertainty can arise from variations in vendor lead times or shop flow times. Thus, once an order is released, the exact timing of its arrival is uncertain. Here, for example, a receipt scheduled for period 3 actually arrived in period 1. Note in this case, the uncertainty isn't over the order's amount but over its timing. The entire order may be late or early. Demand quantity uncertainty is manifest when the amount of a requirement varies, perhaps randomly, about some mean value. This might occur when the master production schedule is increased or decreased to reflect changes in customer orders or the demand forecast. It can also occur when there are changes on higher level items on which this item is used, or when there are variations in inventory levels. In this figure, period 1's projected requirements of 85 actually turn out to be 103 units of usage. Supply quantity uncertainty typically arises when there are shortages of lower level material, when production lots incur scrap losses, or when production overruns occur. This is illustrated also in this picture, where actual quantity received varied around plant receipts. There are two basic ways to buffer uncertainty in an MRP system. One is to specify a quantity of safety stock in much the same manner as with statistical inventory control techniques. The second method, safety lead time, plans order releases earlier than indicated by the requirements plan and schedules their receipts earlier than the required due date. Both approaches produce an increase in inventory levels to provide a buffer against uncertainty, but the techniques operate a bit differently, as we will see in this spreadsheet. The first case on this spreadsheet uses no buffering. A net requirement occurs in period 5 and a plant order is created in period 3 to cover it. The second case specifies a safety stock of 20 units. This means the safety stock level will be broken in period 3 unless an order arrives. The MRP logic creates a plant order in period 1 to prevent this condition. And the final case in this spreadsheet illustrates use of safety lead time. This example includes a safety lead time of 1 period. The net result is the plant order being created in period 2 with a due date of period 4. Most MRP software packages can easily accommodate safety stock since we can determine plant orders simply by subtracting the safety stock from the initial inventory balance when determining the projected available balance. Safety lead time is a bit more difficult. We can't achieve it by simply inflating the lead time by the amount of the safety lead time. In our example, this approach wouldn't produce the result shown as the last case in this picture. The due date for the order would be period 5 instead of period 4. Thus, we must change the plant due date as well as the plant release date. Both safety stock and safety lead time illustrate the fundamental problem with all MRP buffering techniques. They lie to the system. the real need date for the plant order shown here is period 5. If the real lead time is 2 periods, the real launch date should be period 3. Putting in buffers can lead to behavioral problems in the shop since the resulting schedules don't tell the truth. An informal system must be created to tell people what's really needed. This in turn might lead to larger buffers. There is a critical need to communicate the reasoning behind the use of safety stock and safety lead times, and to create a working manufacturing, planning and control system that minimizes the need for buffers. A concept closely tied to bufferings is use of scrap allowances in calculating the lot size to start into production to reach some desired lot size going into the stockroom. It's a fairly straightforward procedure to use any lot sizing procedure to determine the lot size and then adjust the result to take into account the scrap allowance. One issue that arises is whether the quantity shown on the shop paper as a scheduled receipt should be the starting quantity or the expected finished quantity. Practice suggests using the former. This requires, however, that each actual occurrence of scrap be transacted and reflected in updated plans. The overall issue of the scrap allowance is clearly related to the use of safety stocks for quantity uncertainty buffering. One or both of these techniques could be used in a particular situation. The point is, if scrap losses occurs, they must be planned for and buffered. It also means this may be an area where tight control can lead to performance improvements. MRP system nervousness is defined as significant changes in MRP plans which occur even with only minor changes in higher-level MRP records or the master production schedule. Changes can involve the quantity or timing of plant orders or scheduled receipts. This spreadsheet illustrates just such a case. Here, a reduction of 1 unit in the master schedule in week 2 produced a significant change in the plant order for item A. This change had an even more profound impact on component part B. It's hard to imagine a reduction of the MPS level could create a past due condition, but that's precisely what the table shows. How the change caused by a relatively minor shift in the master schedule is amplified by use of the periodic order quantity lot sizing procedure. There are a number of ways relatively minor changes in the MRP system can create nervousness and instability in the MRP plans. These include plant order released prematurely or in an unplanned quantity, unplanned demand, and shifts in MRP parameter values, such as safety stock, safety lead time, or plant lead time values. Nervousness created by such changes is most damaging in MRP systems with many levels in the product structure. Furthermore, use of some lot sizing techniques, such as POQ, can amplify system nervousness at lower levels in the product structures as shown in this spreadsheet. There are several ways to reduce nervousness in MRP system. First, it's important to reduce causes of changes to the MRP plan. It is important to introduce stability into the master schedule through such devices as freezing and time fences. Similarly, it's important to reduce the incidence of unplanned demands by incorporating spare parts forecasts into MRP record gross requirements. Furthermore, it's necessary to follow the MRP plan with regard to the timing and quantity of plant order releases. And finally, it's important to control the introduction of parameter changes, such as changes in safety stock levels or plant lead times. All of these actions help dampen the small adjustments that can trigger MRP system nervousness. A second guideline for reducing MRP system nervousness involves selective use of lot sizing procedures. If nervousness still exists after reducing the preceding causes, we might use different lot sizing procedures at different product structure levels. One approach is to use fixed order quantities at the top level, using either fixed or lot-for-lot order quantities at intermediate levels and using period order quantities at the bottom level. Since the fixed order quantity procedure passes along only order timing changes and not changes in the quantity, this procedure tends to dampen lot size induced nervousness. Clearly fixed order quantity values need to be monitored, since changes in the level of requirements may tend to make such quantities uneconomical over time. A third guideline for reducing nervousness involves using firm plant orders in MRP or in master production schedule records. Firm plant orders tend to stabilize requirements for lower level items. The offsetting cost, however, is the necessary maintenance of firm plant orders by MRP planners. These guidelines provide methods for reducing nervousness in MRP plans. There is a distinction, however, between nervousness in the MRP plans and nervousness in the execution of MRP system plans. Nervousness in the execution of the plans can also influence behavior. If system users see the plans changing, they may make arbitrary or defensive decisions. This can further aggravate changes in plans. One way to deal with the execution issue is simply to pass updated information to system users less often. This suggestion argues against the use of net change MRP systems, or at least against publishing every change. An alternative is simply to have more intelligent users.
Material requirements planning benefits and disadvantages. The obvious point about MRP is that it relates the supply of materials to actual known demand, so it does not need stocks to cover uncertainty or forecast errors. Associated benefits include the following: lower stock levels with supply of materials matched to known demand, savings in capital investment for warehouses, materials handling, and so on, higher stock turnover with no obsolescence, better customer service, no delays caused by material shortages, more reliable and faster delivery times, less time spent on expediting and emergency orders, and more accurate and timely information. MRP can also give early warning of potential problems and shortages. If the MRP schedules show that some materials will arrive too late, the organization can expedite the deliveries or change production plans. In this way, MRP improves the wider performance of the organization, measured in terms of equipment utilization, productivity, customer service, response to market conditions, and so on. There are also some problems with MRP, the most obvious being that it can only be used when an organization has a master schedule that is designed far enough in advance, that is accurate, shows what actually happens, and does not have frequent changes. MRP also needs a bill of materials, information about current stocks, orders outstanding, lead times, and other information about suppliers. Some organizations simply do not record this information, but more find that their information does not have enough detail, is in the wrong format, is not accurate enough, or cannot be transferred between systems. Accuracy is particularly important as there is a huge amount of data processing, with any errors magnified through the repeated calculations. This suggests another weakness of MRP, which is its inflexibility. Some general disadvantages of MRP include the following: it must have a reliable, fixed master schedule prepared sometime in advance. It needs a lot of other detailed and accurate information. Integrated systems must allow the transfer of information. MRP systems become very large and complex. Inflexibility does not allow short-term adjustments. The inefficient order sizes. It can be expensive and time-consuming to implement.
Managing the flow of materials in a contemporary supply chain is difficult and complex. The materials move between firms, warehouses, and distribution centers and can even return to their point of origin with value having been added or for manufacturing. Moreover, the ownership might be different for any combination of the facilities among which the materials can flow. Distribution requirements planning is a technique to help manage these material flows. DRP links firms in the supply chain by providing planning records that carry demand information from receiving points to supply points and returns supply information to the receiving points. Key linkages in the supply network can be integrated through DRP. The logistics activities of transportation, storage in warehouses and distribution centers, and breaking bulk can be incorporated, as can other value-adding activities like labeling, adding country-specific information, or providing special packaging. DRP can be linked into our internal manufacturing planning and control system, both from our suppliers and to our customers. DRP therefore provides linkages that spans the boundary from internal to external manufacturing planning and control system. The linkages that span the boundary from our internal systems to our customers' internal systems are shown in this picture. The link to the front end of the manufacturing planning and control system runs from demand management to the customers and back. Through this link with demand management, demand information is brought into master production scheduling and the sales and operations planning activity. For master production scheduling, the information is important for managing the balance of supply and demand within the current company plans and capacity. For sales and operations planning, the information is combined with other market data and company objectives to develop the company plans. DRP has a central role in coordinating material flows through a complicated physical system consisting of field warehouses, intermediate distribution centers, central suppliers, and customer locations. The role is similar to material requirements planning's role in coordinating materials in manufacturing. Moreover, the DRP information must be integrated into the internal manufacturing planning and control system. This is facilitated by using time-phased information on inventories, materials in transit, and shipping plans. The key task is effectively managing the required flow of goods and inventories between the firm and the market. DRP's role is to provide the necessary data for matching customer demand with the supply of products at various stages in the physical distribution system and products being produced by manufacturing. DRP data provide the basis for adjusting the master production schedule to reflect changes in demand or in the product mix. If manufacturing and distribution system priorities can be adjusted to respond to these requirements, the implications can be evaluated and communicated to customers in a timely fashion. Common records and system integration mean there is complete visibility to see how best to use available inventories and to adjust future schedules. DRP provides a solid base of information to make these decisions instead of relying on political negotiations between field and factory. DRP starts in the marketplace or as close to it as possible. Increasingly, this could actually be at a customer location. Some firms gather information on inventory levels and on product usage directly from key customers, possibly directly from their manufacturing planning and control systems. This knowledge of their customers' requirements provides these companies the opportunity to make the knowledge. In summary, DRP serves two purposes in the marketplace. be it in a warehouse, distribution center, or a customer location. First, DRP enables us to capture data, including local demand conditions, for modifying the forecast and to report current inventory positions. And second, DRP provides data for managing the distribution facility and the database for consistent communications with customers and the rest of the company. And a little bit more about the DRP and the demand management. The demand management module is the gateway between the manufacturing facility and the marketplace. In some systems with field inventories, it is where information on demand is taken in and where product for the field warehouses and inventory status information is sent out. This process requires detailed matching of supply to demand in every location and requires providing supply to meet all sources of demand. DRP is a method for managing the resultant large volume of dynamic information and for generating the information to establish the plans for manufacturing and replenishing the inventories. Plans derived from the DRP information and the resulting shipping requirements are the basis for managing the logistics systems. Here we can see also the relationship between DRP and the logistics activities. Vehicle capacity planning is the process of planning the vehicle availability for the set of future shipments as generated by DRP. Shipping requirements also are used to determine vehicle loads, dispatch vehicles, and plan the resources necessary to receive the goods at the warehouse. By planning future replenishment needs, DRP establishes the basis for more effective vehicle dispatching decisions. These decisions are continually adjusted to reflect current conditions. Long-term plans help to determine the necessary transportation capacity. Warehouses' near-term needs are used to efficiently load vehicles without compromising customer service levels. Data on plant resupply of the warehouses can be used for scheduling the labor force needed at the warehouse. In this and next couple of lectures, we are going to explore the distribution requirements planning techniques. The first lecture in this one, we will see and we will go through the basic DRP records. The DRP system's basic data elements are detailed records for individual products at locations as close to the final customer as possible. Records are maintained centrally as a part of the manufacturing planning and control system database, but continually updated information on inventory and demand are passed between the central location and the field sites either on some periodic basis or in real time, often online. For illustrative purposes, we will consider the record for a single stock-keeping unit at a field warehouse. Regardless of the physical location, central inventory at a plant, distribution center, or a field warehouse, the item's ultimate demand comes from the customer. The warehouse is where the company's internal world of dependent demand must deal with the customer's independent demand. The customer within wide ranges decides how much and when to order. These decisions are usually independent of the company's decisions. Planners in the company, on the other hand, decide when and how much products to make. They also decide when and how much to send to field locations. To link company decisions with the customers, we must start with a forecast. This is recorded in the first row, as you can see, forecast requirements of the basic distribution requirements planning record shown in this table. Even though this first row is labeled forecast, it may contain much more information than the typical average weekly demand forecast produced by a software package. For example, it may have information specific to the customer's buying patterns at the warehouse. It can be directly linked to the manufacturing planning and control system of a customer, in which case the information is not our forecast of the needs of that customer, but a reflection of their current plans. In all cases, however, the forecast requirements are subject to change as conditions change, and the DRP system provides the means to adjust to those changes. The record looks like an MRP record, but there are some subtle differences other than the use of forecast data in the requirements row. For example, because it's for a specific location, it not only provides time phase data on how much and when, but also tells us where. The figure shows a change in the forecast in period 5. This could be due to a revision by someone at the warehouse who has information on local demand, or due to a sales promotion. The fact that these variations can be incorporated into the system at this level provides one of the advantages of using DRP for managing field inventories. The second row shows shipments in transit to the warehouse. Here, one shipment is scheduled to arrive in time for use in period 2. Thus, time for unloading and shelving the products must be accounted for in setting lead time to show the order available for use in period 2. The equivalent row in a manufacturing MRP record is called scheduled receipts or open orders. However, more than the name of the in-transit row is different between manufacturing and distribution. In manufacturing, there is some flexibility in timing of open orders, then can be speeded up or slowed down to a certain extent by changing priorities. This is more difficult with goods in transit. Once a shipment is on a vehicle bound for a particular location, there is little opportunity to change the arrival time. The projected available balance row contains the current inventory balance, 45 for this example, and projections of available inventory for each period in the planning horizon. Here we have 7 periods. A safety stock value of 20 has been determined as sufficient to provide the customer service level desired for this item. The economics of transportation or packaging indicate a normal shipment of this product to this location is 60 units, and it takes 2 periods to load, ship, unload, and store the product. The projected available balance is generated by using the forecast requirements. The process is identical to that used for processing MRP records. Here, the available balance for the end of period 1 is determined by subtracting the forecast requirements of 20 from the initial inventory of 45 and the 25 units at the end of period 1 plus the in-transit quantity of 60 to be received in period 2 minus the forecast of 20 for period 2 give the closing balance of 65 for period 2. Planned shipments are indicated for those periods in which a shipment would have to be made to avoid the projected available balance having less than the safety stock. The projected available balance for period 4, for example, is 25 units. The forecast for period 5 is 30 units. Therefore, a shipment of product that will be available in period 5 is needed. Because lead time is 2 periods, a planned shipment of 60 units. The shipping quantity is shown for period 3. Similarly, the planned shipment in period 5 is needed to cover the forecast of 30 in period 7 because there is only a 25 units project available balance at the end of period 6. The result of these calculations for each product at each location is a plan for future shipments needed to provide the customer service levels the company desires. These plans depend on forecasts, but they incorporate management decisions for shipping quantities and safety stocks in planning schedules. These plans provide the visibility planners need to match supply and demand. Let's continue with one the first DRP technique, time-phased order point. Nowadays, many companies use economic order or shipping quantity reorder point (QNR) procedures based on demand forecast for managing their field inventories. This means decisions for resupply are made independently at the field location with no integrated forward planning. When the on-hand quantity at a location reaches the reorder point, the shipping quantity is ordered with no thought given to any other items ordered, to the situation at the factory or to warehouses, or to when the next order might be needed. Also, QNR assumes a constant usage whenever forecast information is used as the requirements, and a time-phased MRP approach is used to develop planned shipments. It is called time-phased order point. Time-phased order point can be used for constant usage situations and even when the usage forecast varies from period to period. We will use this picture to illustrate this approach. If a QNR system were used, the reorder point for the situation here would be 20 units, comprising the safety stock of 5, plus the demand during lead time 15, assuming continuous review of inventory balances. Simulating the QNR rules for this data would lead to orders in periods 2, 4 and 7. If we use DRP logic, the planned shipments are in periods 1, 3 and 6. Thus, the timing of the orders in the time-phased order point record here doesn't exactly match the expected timing of orders using QNR. The results are, however, very close. The differences would largely disappear if the periods were made small, for example, days instead of weeks, since they are primarily due to the fact that QNR assumes continuous review. This approach is based on the MRP logic of planning a shipment that prevents the ending balance in the period from falling below the safety stock level. One advantage of this technique over QNR is the time-phased order point records show planned shipment data. These aren't part of the QNR approach. In addition, this approach isn't limited to use of constant requirement assumptions. When forecast usages vary, differences between time-phased order point and QNR can be much larger than those here. Not only it is important to have planned shipment data, it is also critical to capture all demand information. Forecast sales requirements are only one source of demand input. DRP can use time-phased order point plus actual order data and service part requirements and interplan demands. All these demand sources can be integrated into the demand data driving DRP. Now let's continue with linking warehouse records. Once DRP records are established for all the field warehouses, information on planned shipments is passed through the distribution centers, if any, to the central facility. This process is sometimes referred to as implosion. The concept indicates we are gathering information from a number of field locations and aggregating it at the manufacturing facility. This is different from the explosion concept in manufacturing, where a finished product is broken into its components. But the process is the same, and in both cases it's based on bills of materials. The record in this picture is for the central warehouse inventory. The requirements here, gross requirements, are for the planned shipments and the two warehouses we used in the previous lectures. This relationship reflects the logic that if there were a shipment of 40 units of product to warehouse number 2 in period 1, there would be a demand on the central warehouse for 40 units in period 1. The demand, however, is dependent, having come from the company's shipping department. It is therefore a gross requirement and not a forecast requirement. We have crossed over from the independent demand of the customers to the demand of the company. The central warehouse gross requirements is shown in the same period as the planned shipment, since lead time to ship, unload and put away the product has already been accounted for in the field warehouse record. For example, the shipment of 60 units of product planned for period 3 in warehouse number 1 allows for the lead time before it's needed to meet forecast demand. The logic for imploding planned shipment information holds also for much more complicated distribution systems. If there were intermediate distribution centers, they would have gross requirements derived from the warehouses they served. At distribution centers, gross requirements are established for any period in which replenishment shipments are planned for warehouses. A primary task at the central facility is to create the master production schedule. The central inventory record in this picture can be used for this purpose. The record shows projected available balances for the central inventory and the planned order releases, which provide the quantities needed to maintain the 50 units of safety stock. The master production schedule is created by using zero lead time and firm plant orders. Firm plant orders are created by the planners and aren't under system control. They aren't automatically replanted as conditions change, but are maintained in the periods and quantities designated by the planners. The master production schedule states when manufacturing is to have the product completed and available for shipment to the field warehouses. In the example here, the master production schedule quantity, or the firm plant orders, has replaced the plant order, although this does not need to be the case. This example implies creating a master production schedule for each end item. This may not be desirable in firms that assemble or package a large variety of end items from common modules, subassemblies, or bulk materials. If the master production schedule is stated in subassemblies or bulk materials, then a final assembly schedule needs to be created for managing the conversion to assemblies or packed products. The resultant records usually don't need to be frozen or firm planned over extensive planning horizons, since they only deal with conversion of bulk material into some specific packaged products. Here, this table on the left shows how this conversion can be managed. These packaged products' gross requirements are exploded from the shipments planned to go to all the field's locations. Packaging this specific product from the bulk material takes one period. Firm plant orders up to the planning phase at period 3 are used to schedule the packaging operations. The record also shows 10 units of packaged product held at the central facility to provide flexibility in shipping to the field warehouses. Tables on the right, bulk material records and MPS, show how the various sizes of packaged products can be combined into a bulk inventory record for creating the factory's master production schedule. In the example, 2 package sizes consume the bulk inventory. The packages are in grams while the bulk item is in kilograms. The explosion process works from packaged item to bulk, but the grams have been converted to kilograms to get the gross requirements for the bulk material. For example, for period 1, 100 units multiplied by 200 grams, which gives 20 kilograms. Here also we have entered the formulas for you. So you can use all those calculations and tables with the formulas. You can download them from the resource section of the lectures. The firm plant orders for the bulk material are the factory master production schedule, stating when the bulk inventory must be replenished to meet the packaging schedules. Now let's continue with the next lecture, managing day-to-day variations from plan. On a daily basis, disbursals for actual customer demand receipts of inventory and other transactions are processed. These transactions are used to periodically update the DRP records. If forecasts and execution of plans were perfect, we wouldn't need to do anything, but adding the new period of information at the end of the planning horizon each time the records were processed. Unfortunately, we haven't found a company where such conditions exist. Here on the left, tables on the left show a more likely set of circumstances. In this example, actual sales vary from 16 to 24, around the forecast of 20 units. The actual sales of 18 in period 1 have no impact on planned shipments, while actual sales of 24 units in period 2 change the plan. The additional sales in period 2 increase net requirements, which leads to planning a shipment in period 3 rather than in period 4. Sales in period 3 were lower than expected, so net requirements are less and the planned shipment in period 5 is changed to period 6. Thus, the gross to net logic results in modifying shipping plans to keep them matched to the current demand situation. One negative aspect of the logic is clear from this example. Actual sales deviations around the forecast were reflected in changed shipping plans. These changes could have a destabilizing impact on the master schedule and shop. Two techniques for stabilizing the information flow are firm plant orders and error add-back. Tables on the right applies the firm plant order shipment concept to the warehouse example. By using firm plant shipments, the record shows the what-if results of maintaining the present order pattern. By using DRP records to display this pattern, we generate standard exception messages. For example, if a present plan violates a stated safety stock objective, exception messages highlighted. In these tables, record for the period 3, the firm plant shipment of 40 in period 4 isn't rescheduled to period 3, even though the projected available inventory balance for period 4 is less than the safety stock. Thus, the master scheduler can review the implications of not changing before deciding whether changes should be made. In this case, the decision might be to opt for consistency in the information, knowing there is still some projected safety stock and the next order is due to arrive in period 5. An alternative for stabilizing the information is the error add-back method. This approach assumes forecasts are unbiased or accurate on the average. This means any unsold forecast in one period will be made up for in a subsequent period, or any sales exceeding forecasts now will reduce sales in a subsequent period. With this method, errors are added or subtracted from future requirements to reflect the expected impact of actual sales on projected sales. The tables on this sheet applies this concept to the warehouse example. Note that the plant shipments are under system control. Firm plant orders aren't used. This example's records show the plant orders in exactly the same periods as in the firm plant shipment case. Adjustments to the forecast requirements ensure stability in the information. It's apparent this technique's effectiveness diminishes if the forecast isn't unbiased. For example, if the reduced demand in period 3 and 4 is part of continuing trend, the procedure will break down. DRP will continue to build inventory as though the reduced demand will be made up in the future. This means forecast must be carefully monitored and changed when necessary so the procedure can be started again. One convenient measure for evaluating forecast accuracy is the cumulative forecast error. If this exceeds a specified quantity, the item forecast should be reviewed. For example, in period 4, cumulative error has reached a positive 7, a value, here you can see, a value exceeding the safety stock. This might indicate the need to review the forecast for this item. Now let's cover DRP management and some issues. Here on this slide we have shown conflicting functional objectives and their impact on inventory, customer service and total costs. This picture illustrates some inherent conflicts that need resolution in an integrated manufacturing planning and control system. These conflicts are particularly real when DRP is part of the overall manufacturing planning and control system. In many companies, minimization of transportation costs, for example, is a transportation department's objective. The resultant impact on other parts of the organization is often not clearly understood. In a comprehensive manufacturing planning and control system with DRP, linkages across functional boundaries are encouraged, but organizational support and evaluation measures need to be established that will minimize suboptimization of overall enterprise goals. Many companies have implemented a materials management form of organization to help align responsibilities to the material flow needs. Materials management organizations are responsible for all aspects of materials, from purchasing to final distribution to the customers. As firms improve manufacturing planning and control systems either through more comprehensive approaches, such as DRP, or through such enhancements as just-in-time, emphasis shifts from material control to material velocity. Basic discipline and data integrity aren't abundant. Time and responsiveness become the most important objectives. Implied is a need to reduce the organizational fragmentation that has built-in time delays. New organizational structures will increasingly be required, ones with overarching authority to dictate actions that provide rapid response to customer needs. Here we have illustrated where DRP fits within the supply chain management concept, showing the many organizational entities that need to be coordinated. The ideas parallel those of materials management, but they focus on the process of building the product. Coordinating this chain requires integrated information in distribution requirements planning form and an organizational form such as materials management. Key to implementing a manufacturing planning and control system with distribution requirements planning, regardless of the organizational form, is developing planners. The titles can vary in different companies. Planners establish firm plant orders, evaluate alternative means to solve short-term problems, coordinate problems that cross functional boundaries, and help evaluate trends. They are also responsible for checking feasibility of changes, monitoring data integrity, and assessing the impact of new situations. We already discussed changing conditions due to uncertainty in demand and the techniques that help to deal with them. Other problems come from changing market conditions, product lines, or marketing plans. Examples are product substitutions, promotions, changes in warehouse locations or customer assignments, and controlling the stock obsolescence. DRP records help us solve these problems. We will describe some of these alternatives. So the first one is on this sheet. It presents a sales promotion served by a warehouse. For simplicity, we consider only one product at a single warehouse and the product's packaging line. The process starts with modifying the demand forecast at the warehouse. In the example, the promotion is planned for weeks 5 through 8. The impact is estimated to double sales from 20 to 40 during the first 2 weeks and to have a reduced impact during the next 2 weeks. Now the promotion steals from demand in weeks 9 and 10. The safety stock has been left at 5 units for the promotion period, although it might have been increased. Stock for the sales promotion is planned for delivery in the weeks in which needed, although it also might have been planned for earlier delivery if there were a need to set up some special display area. The shipping quantity is in multiples of 20, representing a shipping carton or pallet load. Planned shipments are exploded to the packaging record. Using the firm plant orders, the planner has scheduled product packaging at a constant rate of output for the next 5 weeks, just under the capacity of the packaging line, building inventory in anticipation of the promotion. The anticipation inventories are shown as remaining at the packaging facility, but they might be sent to the field if space is available or if a truck is on its way with available cargo space. The pattern of inventory build-up could be different depending on the trade-off between level production and varying the production levels. The DRP records facilitate both planning the build-up and analyzing alternative ways to meet the need. Our second example deals with a warehouse closure. Firms often change distribution systems, so closing warehouses and changing shipping patterns are ongoing activities. Here in this sheet, Warehouse 1 is scheduled to close at the end of 4 weeks, and Warehouse 2 is to start supplying the customers. Again, the process of managing the cutover starts with the forecasts. The requirements at Warehouse 1 stop at the end of week 4 and are picked up by Warehouse 2, reflecting the timing and quantities of the close down and transfer. In the example, Warehouse 1 would normally have had a planned shipment for 60 units in week 3. The planner has overridden the plant order with a firm plant order for the exact need, reducing safety stock to 0. Now the system plans an order to restore the safety stock, and eventually the planner will need to change the safety stock parameter to 0 in order not to send the wrong signal to the master production schedule. As time goes on, the actual quantity needed for Warehouse 1 may well be different, but there are 2 weeks before the exact determination must be made. The planner may decide to send even less to Warehouse 1 because it might be easier to pick up some unsatisfied demand from Warehouse 2 than to deal with the remained inventories at Warehouse 1. The point is, DRP systems provide visibility for solving these problems. Even though the exact quantity to be sent to Warehouse 1 won't be determined until week 3, the amount produced and made available to send to either warehouse will be correct, since planned shipments from both are exploded to the requirements of the central facility. The main questions are how to divide the available stock between the 2 facilities and how to manage the transitions. And finally, controlling inventory of products whose shelf life is a concern. One aspect of this problem is to use strict first in first out physical movement and to make this part of the training for warehouse personnel. And the second way to deal effectively with shelf life problems is to identify those products that may be headed for a problem before it's too late. One way to do this is to use DRP records and built-in exception messages to flag potential shelf life problems.